Positioning control of pneumatic system using adaptive algorithm. Hi, my name is Nashakira Winter Mayase and my supervisor is IR Datulaban bin Abdullah. Okay, in this presentation, I focus on 5 contents which are introduction, literature review, methodology, simulation result and conclusions. Okay, for introduction, I focus on problem statement, objective and scope of project. Okay, for problem statement, the most common problem in pneumatic actuator system is caused by non-linearities of the system, such as the high compressibility of air, frictional force, dead time, and dead bend, so that the actuator cannot get the desired displacement without overshoots. 3. Objective, which is to model a pneumatic system using mathematical modeling approach to design an adaptive controller to control the positioning of the system using MATLAB or Simulink, to analyze the performance of the design controller via analysis of steady-state error, stability conditions, and transient response of the system. The scope of project identify and construct the mathematical modeling of pneumatic system based on the parameter estimation by considering its dynamic characteristic and friction. Study the proposed control design that will be simulated on the MATLAB or Simulink. Study the performance of the system with the proposed technique. Analyze the performance of the system. So in literature review, I focus on the type of controller. First is proportional controller. The advantage of P controller is P controller helps in reducing the steady state error, thus make the system more stable. The slow response of the overdamped system can be made faster with the help of this controller. Integral controller. Due to their unique ability, I controller can return the control variable back to the exact set point following a disturbance. That's why they are known as reset controller. Derivative controller. The major advantage of D controller is that they improve the transient response of the system. So, proportional integral and proportional derivative controller. Generally, it is said PD controller improve transient performance and the PI controller improve the steady-state performance of a control system. Proportional integral derivative controller, PID can provide better tuning. In the olden days, the PI controller was one of the best choice of control engineer because designing tuning of parameter of the PID controller was a little bit difficult. Nonlinear proportional integral. The anti-interference of NPID controller is good, which quickly recovers steady state. Hence, we can adopt appropriate nonlinear function to improve traditional PID controller performance and solve contradiction in overshoot and rapidity. It can obtain more excellent control quality in general excitation system. Methodology focus on flowchart, software development, controller design, and stability analysis. Okay, this is my flow chart. Problem statement, literature review, modeling approach, model validation if no re-evaluate design, if yes, design simulation, run simulation if no troubleshoot, if yes, implementations and performance analysis, then comparison and evaluation. Okay, software development. I use MATLAB to analyze data, develop algorithm, and create model and application in Simulink for the system using this software. Thus, this software used to design control for pneumatic system. Simulink is an add-on product to MATLAB, provide an interactive graphical environment for modeling, simulating, analyzing of dynamic system. For modeling, Simulink provide a graphical user interface (GUI) for building models as block diagram. This is my controller design of PI and NPI. As shown is the transfer function where the proportional gain is 9.3144, the integral gain is 3.9541, and the derivative gain is 0. Okay, the stability analysis focus on 5 analysis which are a gain margin indicator where GM is higher than 0 dB, preferably GM is higher than 4 dB but lower than 10 dB. Routh-Hurwitz criterion focus on its criteria, which is no sign change to be stable. Nyquist plot, the graph is not encircled at -1. Popov plot not passing beyond Popov stability line. Pole zero plot, all poles need to be at left half plane. Okay, the simulation result. focus on transient response, dot plot diagram, pole zero plot, Roth-Hurwitz criterion, and pop-off plot. Okay, the transient response. Okay, as you can see, this is the result from the Simulink. Okay, it shown are the DEM. The DEM system are the most practical and most commonly used. The main reason is they will ensure the system always reaches the desired end state with some overshoot. Even though there is overshoot, the damping eventually brings the system to the desired state. Okay, this is the transient response parameter. As you can see, the peak time of NPI is higher than PI. Cmax NPI is higher than PI. The rise time is NPI is higher than PI. Overshoot NPI is higher than PI. The C final NPI is higher than PI. The steady state error NPI is lower than PI. The settling time NPI is lower than PI. Okay, the gain margin indicator shown that the gain 25.6 at dB at the frequency of 0.0464 radian per second equal to negative 180 degree is greater than 0 dB, meaning a positive gain margin. Then the closed loop system is stable. The phase 93.9 degree at the frequency of 0.00358 radian per second equal to 1 is greater than negative 180 degree, meaning a positive phase margin. The closed loop system is stable. Then Roth-Hurwitz criterion, the PI and NPI show that all the elements of the first column of the Roth array are positive. There is no sign change, so the control system is stable. Okay, the Nyquist plot. Based on the diagram, it is found that the system is stable because Nyquist diagram not n circle at -1. Okay, pop-off plot. Based on the figure, the system is asymptotically stable because not passing the pop-off line. The pole zero plot, usually a zero is represented by a O small circle and a pole by a X cross, so a system is stable without reservation if it only has pole in the left half plane. So as conclusion, is it achieving the objective or not? Okay, the objective one, to model a pneumatic system using mathematical modeling approach. Since the transfer functions have been obtained, thus the objective one successfully achieved. Second objective, to design an adaptive controller to control the positioning of the system using MATLAB or Simulink. Since the control scheme have been produced, it is shown that the objective 2 also successfully achieved. Then third, to analyze the performance of the design controller via analysis of steady state error, stability condition, and transient response of the system. Since the transient response parameter have been obtained, thus the objective 3 successfully achieved. So as conclusion, all the objectives have been achieved. That's all from me. Thank you.